Hello, Science Alliance. I am Lara. This is Theory of Science. I am actually trained to teach physics up to A level, and that is what I get to do in these lessons. I stream an all ages show with printouts, which are optional. I do a Lego show, which I just finished, where I have to wear a silly costume, and this one is our IGCSE lesson. Right, we've been learning about energy. It's a really weird one today, I must admit. It's not an intuitive one today because we're talking about work done and how physicists talk about work. It's just not how your regular people talk about work. So let's go back a little bit. We've been talking about heat, right? I've got a metal spoon here for demonstration purposes. We've been talking about heat. Heat is when, it says here, energy is transferred because of a temperature difference. Heat is when energy is transferred because of a temperature difference. We haven't actually put it in that language, but hopefully if you've been to the previous lessons, you can see how that makes sense. We've picked up things like metal spoons and talked about how they feel cold, and they feel cold because your body is warm and heat is being transferred from your body to the spoon. And that is because there's a temperature difference, right? If the spoon was perfectly at your body temperature, then you wouldn't pass energy to the spoon. You see? You get it. The heat is flowing from your hand to the spoon because there's a temperature difference there. So scientists, the sort of natural historians, people in the world have known about this for quite a long time. People were sort of fairly comfortable with heat. We've got thermometers, we can measure it. When we started making machines, people were kind of aware that energy was happening. We've talked a bit about energy stores before. We'll talk about them later. When stuff gets lifted up, it's like energy is being transferred to it, right? Because it's moving, but how much energy? Like how do you measure that? Because there's no temperature difference. Well, the philosopher, how do you say it? I've seen his name written down loads of times before. Descartes. He's French, isn't he? The philosopher Descartes, in 1637, he thought about this. He said, I'm misquoting him horribly to make the numbers easier, but he said something like, it takes the same effort to lift 10 grams, 20 centimetres, as it does to lift 5 grams, 40 centimetres. He said something a bit like that, which sort of led us to this idea of work. So work is done. Work is basically energy being transferred when it's not because of a temperature difference. Work is done when energy is transferred mechanically, like by a force. So if you push or pull something, and this is a really useful definition for us today, when a force causes a displacement of an object, you say that work is done on the object. So not all energy, not all situations where there's a force is work being done. Work, you would say, is being done when a force causes a displacement. You okay with what displacement is? You might not be, because I say you can do the lessons in any order. We are using some language from the forces lessons today. In forces, we looked at how displacement is, it's essentially like how far something has moved in a certain direction. So if my hand is displaced to there, it just means it's moved to there, yeah, for today. Okay, a couple more slides and then we'll get on to this fascinating, that was sarcasm, baking tray, Lego brick activity. So we say that forces do work to transfer energy. So if you push a box along the ground, for example, then you are doing work. Say the force of your push is 4 newtons, you displace the box, you move it, so you would say that you have done work on the box because you've used a force to transfer energy to the box. Huh? I'm just going to kind of keep saying it until we get it. So this crane, for example, if this crane is running on electricity and it's lifting this bar into the air, we'd say it is doing work. It's transferring energy from its chemical energy store to the metal bar's gravitational store, because it's making the metal bar get higher and higher and higher. So it's applying a force and it's displacing the metal bar in the direction of the force, like the tension in the rope, if you like. It's not a rope, is it? But you know what I mean. There's tension in the rope, which is the force pulling it up, and it's being displaced in the same direction as the force. So that is work being done. Right. I was thinking about how we make this a bit more interactive for you. Have you got a baking tray and a Lego brick? Okay. Oh, very quickly, because Cambridge want you to know this if you're doing a certain GCSE. Electrical work is a thing as well. You would have to look that up in your own time if you were doing the Cambridge spec. Current flowing, you would say does work against the resistance of a wire. Moving swiftly. Oh, yeah, we'll do this first, okay? So get a baking tray. Get a piece of, I said to get a piece of Tupperware. I'm using a spice jar on its side here. Can you prop up the baking tray on the spice jar or the bit of Tupperware or whatever you're using to make a little slope like this, okay? Can you push the Lego brick along the baking tray? So I'll give you 2 fingers, that's perfect. Let's sort of keep this simple and just talk through this. Are you doing work on the Lego brick, first of all? So you're pushing the Lego brick up a slope. Are you doing work on the Lego brick? That's my first question. Shall I flip you around so you can see me as well? There we go. Oh yeah, that's better. That's a bit more Maddie Moat, isn't it? It's better telly. If you push a Lego brick up our little slope, are you doing work on the Lego brick? Well, hopefully, yes, you are doing work. So someone in the comments has said, yes, you are doing work, yes, because you have applied a force and the brick has been displaced, it's moved, in the direction of the force. So you are doing work. Nice. How about if you put the tray flat now and then you push it? That's nice to see people agreeing with each other in the comments. What about if the baking tray is flat and then you push? Have you done work on the Lego brick? Shall I speed up a little bit? Okay. You're probably saying yes. Yes, you have done work on the Lego brick. All right, what if you flick it with the same amount of force, okay? So instead of pushing it, let's say you've pushed it with a force of, I don't know, 2 newtons. Let's say you flick it this time with a force of 2 newtons and it flies through the air and lands there. So you could push it right to the end, or you could flick it with the same amount of force and it comes through the air like this and then it lands. Have you done the same amount of work on the Lego brick or more or less? You flick it with the same amount of force. Have you done the same amount of work or... You would say you've done the same amount of work because you've applied a force and you've caused a displacement. So you'd measure the displacement and you'd measure the force and that would give you the answer. That leads us nicely to the equation. We will come back to this weird little setup here, I think. So the equation for work done, you might have even started to get a sense for it now with that Descartes quote. Work done, it's a nice one this, it's okay. It's force times distance moved in the direction of the force. Work done, the amount of energy transferred, because that's what work done is. You're transferring energy to a thing. The amount of energy transferred is the force that you apply times the distance moved in the direction of the force. Can you tell me what the unit is for work done? That's a really mean question if you haven't been to the forces module. In fact, it's an impossible question actually if you haven't started learning about forces yet, so I won't spend very long on it. But we've talked quite a bit in the forces module, and I keep sort of trying to bring these things back again. How we get used to equations, you do equations with numbers. So if like the force was 5 and the distance was 2, then the work done would be 10. But whenever you've got an equation with different units in it, units are like meters or seconds or newtons or joules, you're also doing the same thing to the units. So the unit of force is the newton, and the unit of distance is the meter in physics. Those are just the ones we use. So what do you get if you times newtons by meters? So my kid was looking over my shoulder while I was planning this lesson, and they said newtons per meter. And I said, no, it's not newtons per meter, be careful. In algebra, if you say like 3 times x, you just write 3x, don't you? And if you were writing newtons times meters, then you would just say Newton meter. But the Newton meter, a kind of cool nickname for the Newton meter is the joule, which is what energy is measured in. So I thought, I don't want to confuse you, but I thought, well, we're doing an equation which involves newtons and meters. you might be wondering, well, why do you just call it a joule? Like, that doesn't make sense. But yeah, Newton, meter, and joule mean exactly the same thing. You should say joule in your exam though. Right, let's do a. Yeah, no, I'll show you. I'll be kind. I'll show you the PowerPoint a little bit, and then we'll go back to our baking tray. We would say that this crane is doing work against gravity. It's doing work on the pipe to lift it into the air, and it's doing work against gravity because the direction of the force is in the opposite direction to gravity, okay? If you're pushing a box, then you're doing work against friction because the friction of the ground that you're pushing against is pushing in the opposite direction. When you push a box, are you doing work against gravity? If you push a box along a ground, are you doing work against gravity? This is a tricky question. I mean, I'm supposed to be teaching you this really, so it's a bit mean to make you answer it, but also it's good teaching practice. I'm supposed to make you think before I just tell you everything, or you won't remember. If you push a box, you're doing work against friction. Are you doing work against gravity? Some people in the comments saying yes, you are. Oh, no, because gravity is still working. It's pulling the box to the ground. Oh, that's a good answer. Oh, that's a good answer. So the answer is, brilliant thinking there. No, you're not doing any work against gravity. Work is force times distance moved in the direction of the force. So you're doing work in that direction, like across the ground. Gravity is acting in like a 90-degree angle. So no, you're not doing any work against gravity because you're not doing any work in the upwards direction. I was going to tell you this later, but I'll tell you it now actually before I forget. If you're doing, sorry about the horrible smears, let's just pretend they're not there. If you're doing work on a slope, if you're pushing a thing up a slope, then it gets a bit more complicated. In our forces lessons, and don't worry if you don't understand this, you just have to go back. The forces lessons, which you would do if you were going to do a GCSE. But yeah, if gravity... Do you remember? Vectors are like things that have a direction. So if you were pushing something upwards, we were looking at how you can add up vectors. And actually something being pushed up a slope, that's a force going in that direction. But you could split that up into a vector that went along the ground like that and a vector that went up like that. So if you're pushing something up a slope, there is a bit, there is a component, you would say, of that force that is acting against gravity, but we won't worry about that today. I want to sort of do your understanding really, and then you can go away and study that sort of thing yourself. So the answer is no work is being done against gravity because there's no force acting against gravity because it's just going in a straight line at a 90-degree angle. Right. Let's go back to our baking tray and see how much of that you've understood, because I think it is quite complicated, this. So I tell you what, yeah. This time, whatever Tupperware or object you were using that was a bit higher to make the slope, can you just put it on top of your baking tray and move the Lego brick from the baking tray onto the top of the thing? Have you done work on the Lego brick? Have you done any work on the Lego brick? If you just lift it from the baking tray to the top of the Tupperware or whatever you're using. Yes, you have, haven't you? You've done work against gravity. You've lifted the brick up in the opposite direction to the way that gravity is acting. So pretty much all the work that you've done is against gravity there, isn't it? Until you can plop it onto the brick. What about if you make the slope again? What about if you make the slope? We'll say that the top of this slope is the same height, but this time it's a slope, not a step. What about if you push the Lego brick to the top of the slope? Are you doing any work against gravity? Are you doing any work against gravity if you push this Lego brick to the top of the slope? Yeah, you are. You are doing some work against gravity, right? Because you've moved it up. Yes, beautiful, because the tray is slanted. Yeah, if you've moved something upwards, you must have been doing work against gravity. There will be a component of this force that is acting against gravity, yes. So you've definitely done some work against gravity if you've moved something upwards like that. Which one have you done more work then against gravity? The one where you push it up a slope, or the one where you just lift it straight up? In which situation have you done more work against gravity? Oh yeah, I'm going to stop chatting and give you just a little bit of time to think about that. In which of these situations have you done the most work against gravity? Let's assume that the step is exactly the same height as the tray, as the bit you push it up to on the tray. Which one does more work against gravity? It must be the same, right? It must be the same because they're the same height. The lifting, because the slope is gradually being pushed up, but the lifting does more work. But by lifting it does more work against gravity. But you're getting it to the same height each time, right? So the displacement is the same. Isn't it? Let's do another one. What if you push the Lego brick as hard as you can against the table? If you push the Lego brick as hard as you possibly can against the table, are you doing work in that situation? Have you got it? I don't want to bore you, but I also need to give you time to think. If you push a Lego brick as hard as you can against the table, are you doing any work? It sure feels like I'm doing work. It's very tiring. No, you're not, because there's no displacement. It's force times the force times the direction of the displacement, and there is zero displacement because the thing hasn't moved. So it seems really weird, but you haven't done any work. I suppose if you think of work as being the energy transferred, then it makes sense, doesn't it? Like you can kind of, it's intuitive that we haven't transferred any energy to the Lego brick. Or I suppose we possibly have, but it's a temperature. It's due to a temperature difference. Oh, right, that's weirdly tiring. Okay, I've got some questions for you. And to be honest, these questions, guys, these questions aren't my finest hour. The T-Rex question, if you've got the printouts, I've had to change the T-Rex question because I suddenly realised that I've just got myself in a bit of a muddle. I was trying to make it cool and realistic, but it's not going to work. And I also didn't want to assume that you'd done the forces lessons. So if you've got the printout, you're going to have to read the T-Rex question off the sheet. I'm really sorry. Here we go. So work done is the force times the distance moved in the direction of the force. So question number one, a cat weighing 20 newtons falls off a 4-metre high shelf. How much work is done by gravity? Not a trick question. If the cat weighs 20 newtons and it falls off a shelf and the shelf was 4 metres up, how much work is done by gravity? Question number two. Found a cocktail stick, what fun. A crane lifts 8,000 newtons onto a 20-metre high scaffold. How much work does it do against gravity? Question number three, this is the one that you can't read on your sheet, sorry. Look at the screen, guys, look at the screen. A T-Rex drags a 30,000 Newton Triceratops 100 metres to its nest at a constant speed using a pulling force of 40,000 newtons. Just go with it, okay? Just go with it, I'm sorry. How much work does the T-Rex do? Question number four. Raphael lifts a 300 Newton weight and shifts 300 joules of energy from his chemical store. How high does he lift the weight? Question number five. An acrobat weighing 900 newtons sits on a hoop and is lifted 18 metres into the air. How much work does she do? Question number six. A box weighs 5 newtons. A woman pushes it with a force of 4 newtons. It goes 2 metres. How much work is done against gravity? So I've put if you did forces with me. Is distance moved in the direction of the force a vector or is it a scalar? but that's just a bit of revision. You don't need to know what that means. And the question that, if you've only done this lesson with me, I'd like you to think about is, can you see a problem with question 4? Actually, no, you would have had to have done some more energy lessons, really. If you've done a few lessons already on this, can you see a problem with question 4? Your answer is correct. Well, your answer isn't correct, actually. But you can only work out one answer with the information that I've given you. But the answer you've got, well, I've said too much. Can you see a problem with it? Just enjoying looking at the comments. Oh, nice one, Karen, yeah. Slope is gradually being pushed up. Yeah, exactly. So you're quite right, but I think very good for thinking about friction, yeah. It's just the friction. Yeah, I see what you mean. Yeah. Okay. You can hear, I've just been fiddling with my whiteboard, scratching the grossness off with a bit of cocktail stick, and I've completely lost track of how much time I've given you. Is it time to move on? Should we move on? Yeah? Is that all right? Watching the comments to see if anyone, there's no one commenting, which is sort of a good sign that you're all busy working. I will say in this bit that if you are watching live, then on my Facebook page at the moment, there is a post up saying that if you don't like or you can't comment on YouTube, then you can come over and comment on Facebook. That'd be nice. I like my Facebook comments. It'd be nice to see you. All right, should we go through the answers? So, a cat weighs, it's true, yeah, I mean, we didn't even get into weight. I haven't re-explained what weight means, but your weight is basically how much force is pulling you down towards the ground. So a cat weighing 20 newtons falls off a 4-meter high shelf. How much work is done by gravity? It would be 20 newtons times 4 meters, which is 80 newton meters. That's probably what I would write in the exam, to be honest, so that I knew that I'd got the equation right, and then I would also quickly add 80 joules, all right? So that's how much you could say, how much energy is being transferred to the cat. A crane lifts 8,000 newtons. Was that right? Did I go too fast? So that answer was 80 joules. A crane lifts 8,000 newtons onto a 20-metre high scaffold. How much work does it do against gravity? Again, you would do 8,000 newtons times 20 metres, which is 160,000 Newton meters. But then I would change that to joules because the Newton meter and the joule are the same thing. So that's how much energy got transferred, or how much work it did against gravity. A T-Rex. Oh yeah. So this was the question that I had to change. So this bit is incorrect now, but the answer that you should have got was you needed to times the pulling force by the distance that the Triceratops had done. I was just trying to be cool. I was trying to make it interesting, okay? Because I didn't know that Triceratops and T-Rex existed at the same time and that T-Rex did eat Triceratops. We have bits of Triceratops that found inside the T-Rex. Anyway, you had to do 40,000 newtons times 100 meters to get 4 million Newton meters. And then I would write 4 million joules. If you wanted to write that in kilojoules, do you know what you'd do? You would have to do that. Possibly in an IGCSE physics exam. I don't usually I assume that you're going to just learn the maths on your own in your own time, so I don't tend to push it with the maths because you might not have learned it yet. But if you want to change 4 million joules into kilojoules, there are 1,000 joules in 1 kilojoule, right? 1,000 joules in 1 kilojoule. So if you put this into kilojoules, it's going to be a smaller number. And you divide it by 1,000. So basically you just take 3 zeros away. So it's 4,000 kilojoules. If you wanted to change it into megajoules, there's 1 million joules in 1 megajoule. So you divide that top number by 1 million, you take 6 zeros off, and it's the same as 4 megajoules. So that would be fine as well. They might ask you to do that in the exam, don't they? Next one. Raphael lifts a 300 Newton weight. This is one that I said there was a problem with, and could you see the problem? And shifts 300 joules of energy from his chemical store, right? So Raphael eats food, they breathe oxygen, you get a chemical reaction there. So that shifts 300 joules of energy from his chemical store. How high does he lift the weight? So all you could do, because the only information I gave you was that, is to rearrange this equation to get the distance moved in the direction of the force. So you had to do work done, 300 joules, divided by the force, which was 300 newtons, to get 1 metre. Let's come back to that. An acrobat weighing 900 newtons sits on a hoop and is lifted 18 metres into the air. How much work should she do? She doesn't do any work. In fact, 0 work is done in both these cases. If you're pushing a box horizontally along the ground, no work is being done against gravity because no component of your force is acting in the opposite direction to gravity. And the acrobat here, she's just acting like a weight, isn't she? Like she has a weight, but it's actually the person who's pulling the rope or whatever and lifting her into the air that is doing the work. The thing isn't moving in the direction of her force. So she has not done any work there. Is that all right? It's a bit brutal, wasn't it? So the problem with the Raphael question, we've done this. We did this quite a while ago. Oh, I'll just take you through the forces one. If you did forces with me, then yes, distance moved in the direction of the force is a vector, because a vector is basically distant. Well, a vector is a number and a unit and a direction, right? So distance is a scalar. You would just say I travelled 5 meters, whereas displacement is a vector because it's distance with direction. So if you said I travelled 5 meters to the east, that would be a displacement. Okay, the acrobat. So this Raphael guy, he's lifted a weight, he's shifted 300 joules of energy from his chemical store, and he's pushed with a force of 300 newtons. How high does the thing go? You can't assume, can you, that all of the energy that he shifts goes into doing work against gravity, because we've looked at how every time anything moves, basically you get some sort of heating effect. Like some of Raphael's 300 joules that he shifts will go into heating the air around him, will go into heating the air basically. So all you could really say is that he would have lifted it slightly less than a metre. Because, yeah, that's not how energy works. That would be a perfectly 100% efficient machine, which isn't a thing, which we'll talk about in a couple of weeks' time. Okay, let's see how much of that you've understood. These with just 2 questions. These people have got this 4 Newton box to the top of the hill. How much work has each done against gravity? So you've got a slope here that is 5 meters long, and the box is at the top of the slope, which is 3 meters high. And here you've got another slope, but this time it's steps. So 0.5 meter long and 0.5 meter high steps. And again, it's 3 meters high, the top of the box. Which one of these people did the most work against gravity? Now, this question, to be honest, it's a very flawed question. I found it really difficult to write questions for you. I should have kept it more simple, because we get into things like, well, how much force was used? How much friction was there? How much time did it take them? It's a bit... What I'm trying to get at is work done is the force times the distance moved in the direction of the force. So certainly the displacement of the box is the same. It's 3 meters. So I've said that it's 12 joules in each case. But if you have done a lot of revision and you want to argue back at me about that, then send me a message. Have a look at this one. I'm quite happy with this one. I think this sort of gets the point across anyway for the last question. You've got 2 identical boxes that are moved onto a table. The arrows show the movements the people did to get them there. So one person has just moved their box onto a table, and one person has moved their box very high into the air and then done a kind of loop the loop, and it's ended up on the table. And the first box is A and the second box is B. Your questions are, which person did more work against gravity? A, B, or they both did the same amount of work? I might just ask you that one to start with, actually. Which person did more work against gravity? A, B, or they both did the same amount of work? Yeah, I don't think a physicist would be very happy with these questions. I've made a lot of assumptions. But I think for our purposes, this is I think this is all right. It gets the point across that I wanted to get across. Okay, so a lot of people in the comments saying B. So my next question is, which box has more gravitational potential energy? If you came to the first energy lesson that we did, which box has more gravitational potential energy? So the answer is making a lot of assumptions that we're not talking about. Person B did more work against gravity because they moved the box higher. Delighted in the comments to see someone thinking about time and how long the box was in the air for. The equation for work doesn't have time in it, does it? It only has force and distance. But we will talk about time later because we need to talk about power. But the reason this person has done more work is because they moved it a higher distance. They then moved it down again. Maybe they were doing an awesome dance. But they've done more work against gravity overall because there's been more displacement, again, in the direction against gravity. But the reason why I think a lot of people on Facebook got caught out by this and were saying it's the same is because they're thinking they do now have the same amount of gravitational potential energy. Yes, they are both, and we'll do a whole separate lesson on gravitational potential energy. But yeah, that is true. They are now sort of storing the same amount of energy in their gravitational potential energy stores. This person has done more work, but not all of the energy transferred has been transferred to the gravitational potential energy of the box, has it? No. Right. Phew! That is the end of this IGCSE physics lesson about work done. So next week, we finally go back to our energy stores. We spent a whole first lesson talking about gravitational potential energy and elastic potential energy. We're going to go back to that. Now we've got hopefully a sort of better idea of what energy is. And we'll talk about pathways and flow diagrams and all that stuff. And then we get to talk about how efficient machines are. Right, I'm just going to go over to my Facebook page and see if anybody has left me any comments. A lot of you have been leaving me lovely comments on this actual... I love like when you always put, oh, I agree with blah, blah, blah. It's really cool. It's nice to see you actually using the comments to kind of compare notes and chat. You do that very well at IGCSE. Right, yeah, I'll just see if anyone's come over to Facebook, leave me a comment. I suppose I should say, because it is how I earn money entirely, if you happen to be new, I mean, you're probably not, right? But if you are new, thank you so much for coming. How this job works is I'm trained to teach physics to A level. I've got a science degree, and there are some comments, brilliant. And I just stream everything for free. So I started it in lockdown, and then you started paying me just because you were choosing to, and now you're still choosing to pay me, so it is my job. So if you go to my About section, you find this a link to this website called Coffee, or you can just click sign up. Hopefully I've put sign up buttons everywhere now. If you're on my website or you're on my Facebook page, you will find a button that says sign up. You send me £5 a month. I send you really, really nice things like diffraction glasses, an instruction sheet, and Theatre of Science magazines. And yeah, that's how it works. Hopefully £5 a month isn't too much from you for what I offer, because I do a all ages lesson as well and a Lego show. Hello Bastian, I thought it'd be you. Hello Willow and Darcy and Jacob and Kai and Lachlan. Oh, hello, that's nice to see. All the regular names, brilliant. Oh, very good. Yeah, that's it. Gives me money. Thank you very much. I will see you all next week for another IGCSE physics lesson. And if you're watching live, another lesson about the oceans and a lesson about, well, a show about sea lions versus seals. Facebook's gone all weird. There we go. Right, excellent. Okay. Thank you for having me. That's a nice thing to say. See you later, you lot. See you later, YouTube commenters. Thank you for making this lesson more interactive for me. That was fun. Oh, it's Orla. Bye, Orla. Lovely to see you. I'll see you all